In the last class, we discussed about uh, what are the features of important features of operating system. In that, we detailed discuss about what are the scheduling algorithms, what are the different scheduling algorithms available. Major ones: clock-driven scheduling, okay, weighted round robin, priority, okay, earliest deadline first, and slack time. Okay, of course, first come first serve. Okay, several type of schedules are there depending upon the requirement. Okay, uh, similarly, in the next topic, we discuss about resource allocation. What? Resource allocation. Resource allocation is there. Okay, and it not only restricted to that only to uh, the real-time operating system, that entire unit. Okay, that the entire unit is uh, and it's clearly mentioned with step by step, okay, in this today's class. Okay. See here, 1 minute. So this slide is not properly open. Just a minute. Okay, I want to give you the detailed information. Okay. Otherwise, I will share that window. See here, this is the unit 4, the real-time operating system. In that, okay, this is the entire outline of that unit 4. Okay, what are the contents available in that RTOS? First one is the architecture of the kernel, and what are the features? Okay, the remaining all of the features of that RTOS. Okay, what is the basic architecture of the kernel, and what is the task scheduler, and what are the task scheduler functions, ISR, interrupt service routines, semaphores, mailboxes, message queues, pipes, events, timers, memory management, and next one is introduction to micro cost to RTOS. Okay, micro cost to RTOS. Okay, they are very advanced. Okay, kernel structure of micro cost to synchronization in micro cost to inter-task communication is very important. Inter-task communication in micro cost to memory management. Okay, of course, this is the one of the part. Okay, one of these OS, the micro cost to. Okay, what are the different services provided by an operating system? You already know. Okay, uh, every embedded system or every computing device, whether it is a mainframe desktop computer or an analog computer or digital computer or an embedded, whatever it may be, the system needs a piece of software using which the user interacts with an hardware. That is called API. Okay, API nowadays, that is API, okay, or GUI to interface with that system. Okay, and basically the embedded system is defined as an embedded system as a combination of that hardware and software. uh, Through this hardware or through the software, we interact with that hardware or software. Okay, Each job is done by invoking the application software package. Okay, and without application software, is it possible? No. Okay, that is the point here. Each job is called a process. Already you know. Each job is called a process. The process is called a thread. Okay, and the multiple processors are treated as in threads. Okay, each job is called process in desktop system, and each job is called task in embedded system. That is uh, okay. The minute difference and keen observation between the embedded and non-embedded systems. Okay, what is the observation here? Each job is called process in desktop systems, but non-embedded systems, and each job is called task in embedded systems. Okay, that is the difference between the process and task. Each task needs some memory and needs some IO device. Okay, and IO has to do the following functions. Okay, what are those functions? Process or task management, or process management or task management. Okay, why? Because process or task. Process in desktop system, that a piece of executing program, that a piece of executing program is treated as a process, whereas in embedded system, that a piece of executing program is called a task with respect to hardware. Okay, and memory management, IO management, including managing file systems. File system management is very important. Okay, and providing the services to the applications and providing the user interface and the GUI. Okay, and these are the common services provided by any operating system. Okay, and not only limited for the RTOS, it is common for every operating system. Okay. And these operating systems are basically divided into a different categories as a single tasking or single process OS or single processor. Okay, and next one is okay, single tasking OS versus multitasking OS. Okay, single user OS versus multi-user OS operating system, command driven OS versus GUI based OS. Okay, nowadays we are always prefer and we always okay interested to use that GUI based OS only. Okay, because of that user friendliness. Okay, that is the operating system is divided into different categories as these three parts: single tasking versus multitasking, single user versus multi-user, command-driven OS versus GUI-based OS. Understand? The next point: as compared to desktops, embedded systems have a special requirements as reliability. That is very important. Okay, and multitasking capability with okay hard or soft deadlines. Okay, that is called a time constraints. Okay, and it needs the embedded system we are always expecting is a compact. Okay, our mobile phone is the best example for embedded system, and that mobile phone is as thin as possible, as thin as possible. Okay, we always interested to hold that very thin mobile phones. Okay, rather than bulk or thicker mobiles. Okay, and that's why there is a small footprint, and that compactness is always possible within small footprints. Okay, support diskless systems. Okay, floppy disk or something CDs or DVDs. Okay, okay, that is the diskless systems. Okay, and simply data transfer is only through GUIs. Okay, is not okay. Of course, um, pen drives, hard disks. Okay, of course they carry the bulk information, but we are always interested to carry the information without any electronical or mechanical or something. Okay, those devices. That is called a support, and the embedded system must support the diskless systems, portability, okay, scalability, and support for standard API. Okay, and these are the common features we are expecting from the operating system. Of course, you know that hard and soft real-time systems. What is meant by hard and what is meant by soft real-time systems? Okay, the hard or soft real-time systems are always classified according to okay, timing deadlines. Okay, okay, one second. Okay, we already discussed about this topic called hard and soft real-time systems. What is the difference between the hard real-time system and the soft real-time system? What is the key point? Hard real-time system is always the time constrained on time. Okay, soft real-time system. Okay, these two are already explained with beautiful examples. Okay, so okay, listen here. What they want to try to explain this hard and soft real-time systems. The hard real-time system is strict about adherence to each task deadline. Okay, when an event occurs, it should be serviced with the predictable time at all times in a given hard real-time system. Okay, and it is tightly or strictly time bounded. Okay, and best example is the automobile engine control. Okay, where in earlier we the same concept we explained with a flight control. Okay, here the automobile engine control system and anti-lock brake are the examples of the hard real-time systems. Lock brake. Okay, and next one is the soft real-time systems. Okay, what is the soft real-time system? What it means? Okay, it means that only the precedence and sequence for the task of operations are to be defined and observe time constraints, and a few deadline misses are accepted. Okay, and underline this point as a few deadline misses are accepted. And in soft real-time system, that soft real-time system may accept, okay, with few deadline misses, whereas in hard real-time system never accept that deadline misses. Okay, that is the key difference between the hard real-time and soft real-time systems. Okay, example for the soft real-time system is set-up boxes and digital cameras are the examples of soft real-time systems. Okay, and because of that flick from that camera on time, okay, doesn't leads to any loss. Okay, that is the point here. Categories of an embedded operating systems. Okay, what are different categories of embedded operating systems? First one is the non-real-time operating system. Non-real-time operating system. Okay, non-real-time operating systems, small footprint, but they are not suitable for hard real-time applications. Okay, that is the in general non-real-time. The title itself indicates that is not suitable for that real-time applications. Okay, that is called non-real-time operating system. Okay, that small footprint, but they are not suitable for uh, hard real-time applications. Example: embedded Linux, Windows XP, Okay, and these are some of the examples of non-real-time operating systems. And next one is the real-time operating system. The real-time operating system strictly suitable for the hard real-time embedded applications. Okay, and where the time is a major concern. Okay, boundaries or deadlines. Okay, that is the real-time operating system. And third one is mobile or handheld OS. Okay, mobile or handheld OS. No, mobile. Okay, or mobile OS is somewhat different. Okay, used in mobile devices such as palm tops, PDAs, and smartphones. Of course, they comes under soft real-time system. Okay, that is the categories of different embedded operating systems. Next, the architecture of the kernel. Okay, actually we discussed about these topics earlier and before your final examinations. Okay. Architecture of kernel. Okay, here not the picture representation is not available. Okay, or okay, leave it. The architecture of the kernel. Okay. The embedded software consists of an operating system and the application software. Okay, that is the point you know. Okay, any embedded software consists of OS and application software, but the OS is not mandatory for a small, very small scale applications. Okay, and the second point is the services provided by the operating system are accessed through API. The services provided by the OS are accessed through API, application interface. Okay, and third point, the API is a set of function calls. The API is always a set of function calls access the kernel objects and services provided by that kernel. Okay, otherwise it's not possible. Okay, the API is a set of function calls access the internal kernel objects and services provided by that kernel. Okay, see here. This is the architecture of the kernel. This is architecture of kernel. Okay, remember this diagram. It is very, very, very important in the final exam point of view also. Okay. What are the different functions provided by that kernel? See here, from the start from the scheduler. Okay, all these are the kernel functions by providing mailboxes, pipes, tasks, semaphores, okay, meet access, timers, ISRs, event registers, message queues, and signals. Okay, we will discuss in detail about each and every function. Okay, and remember this diagram. See here, and one by one. Uh, tasks and task scheduler. Tasks and task scheduler. What is the purpose of task scheduler? Task scheduler. Okay, always assigns some time functions. Okay, time bounding. You see here, the embedded software consists of number of tasks or number of processes. The process object consists of its name. Okay, or the task object consists of its name, and each task is assigned with some unique ID, just like our other. Okay, the task object consists of its name and unique ID and a priority and a stack and a task control block. Okay, remember. Okay, remember these points. The task object consists of its name. Okay, just like our name, and unique ID, just like your roll number, and having your own priority, having some one priority. Okay, and a stack and a task control block. Okay, yeah, these five are very crucial. Okay, regarding to task. Okay. The kernel has its own system tasks with priorities. These tasks are startup task and just like voting. Okay, exception handling task. If of course if any errors arise in between the process, okay, some exceptions are there. That is called exception handling task. Okay, startup task, exception handling task, logging task, and ideal task. Do nothing task. Do nothing is also a one task. Okay, the kernel has its own system tasks with priorities. These are those tasks are startup task, exception handling task, logging task, and ideal task. Okay, each task has to be assigned with some priority, and a mechanism for deciding which task will get CPU time next has to be worked out. Okay, which one is having priority while executing. Okay, this is known as task scheduling. Understand? Okay, did you get the point? What is meant by task scheduling? Okay, and just like what instruction is executed to be next, or which process is taken by that CPU, or which event, or which task, or which process is okay continued by the processor. Okay, based on that priority. Okay, which is decided by a task scheduler. Okay, just like our IPL scheduling. Another important requirement is that one task should not corrupt the data of another task. Why? Because all those tasks are individual, and that intercommunication between the tasks are very, very important. Okay, intercommunication between the task to task is also very, very important. Okay, that's why the another important requirement is that one task should not corrupt the data of another task. Okay. While scheduling the tasks, the number of issues as described below. While scheduling the task, the number of issues are raised. Okay, what are those issues? Okay, those issues are described here as first one. Many tasks make call to a function. Many tasks make a calls to a function. Okay, many tasks okay make a calls to a function. Okay, I will explain the point very clear. Okay, uh, in that re-entrant function and non-re-entrant function. Okay, it is best explained with an example. Uh, okay, on real-time examples there. Okay, I will explain in detail okay, clearly in the upcoming classes. Okay, understand? While scheduling the task, the number of issues are erased. Okay, what are they? Maybe the single task. Okay, at a different tasks may call a single function. Different task may call a single function. Okay, how it is possible to take that function for that different tasks? How it is possible? Okay, many tasks make calls to a function. Okay, in that two types of functions are a re-entrant function and non-re-entrant function. Of course, re-entrant function may allow to use that task, but non-re-entrant function may not allow okay and utilize that function. Okay, that is the problem. Every task requires some resources. Okay, and to perform something, that every task or every process requires some additional resources. Okay, tasks may need to communicate data amongst themselves. That is called intercommunication among the tasks. Okay, intercommunication intercommunication among those tasks. Okay, that is the task and task scheduler functions. Okay, what we learned, task and task scheduler, uh, the main requirement is one task should not corrupt the another task. While scheduling the task, number of issues are erased. Many in that many tasks may call a single function. or every task requires resources. Tasks may need to tasks may need to communicate data amongst themselves. Okay, that is called intercommunication. Okay, especially in an embedded systems. Okay, and what are the different states available in the task? Okay, and is it running state, or is it waiting state, or it is ready to run, okay, or it is in ISR state. Okay, in which state the tasks are there. Okay, that's why that concept called task states is explained here. Task states, okay, especially in an embedded system, each task has to do some specific job, you know. Okay, that's why here we consider an embedded system that obtain data from a serial port. Okay, and here assumption is, okay, I want to take some data from the serial port and convert that data into Ethernet packets. Okay, okay, what's the task here? Just I want to take that serial data, and the collected data, that collected data is converted into okay, uh, Ethernet packets. Okay, and what are that Ethernet packets? Okay, what it contains? That entire data is split into different parts, and each for each data, it is assigned with some start bits, stop bit, or synchronous bits. Okay, header and tailor. Okay, uh, and by the insertion of different synchronous bits and all those additional bits. Uh, and that particular okay, that particular data is treated as a packet. Okay, that conversion, and it will transfer the data from for a longer distances. Okay, that's why, especially for an embedded system, uh, it, suppose it obtain the data from a serial port and converts the data into an Ethernet packets. Okay, what are the different states available here under this assumption? Okay, for suppose ready to run, ready to run. Okay, and I take the serial data. Okay, and serial data and the serial port is not yet connected. Okay, for suppose the pen drive is not connected, or that serial data port is not connected, until that state it is always in waiting, always is waiting. For suppose once that port is connected, now it is ready to run. Okay, and the waiting state to ready to run state. Okay, and now it is ready to run. Okay, once function started, and once function started means running started. Okay, it is always checks for is it available, that port is connected or not, and it is always checks about that source. That's why that is ready to run. Okay, okay, for suppose it is running. So for suppose it is running, for suppose another hyperIT interrupt is there. Okay, so running state to ISR. Once the ISR is completed, again goes to that running state. Okay, after the that conversion is completed, and send the same into uh, uh, that rotor. Okay, again the running state goes to waiting state. Okay, the same is explained here. That sorts the task states. See here, a task can be one of the following states: maybe running state, or maybe waiting state, or maybe ready to run state, or maybe ideal state. The ideal state is also there. Okay, ideal state means do nothing state. Okay, here the task can be one of the following states as a running state. If it is being executed by the CPU, that is called running state. A waiting state, if it is in waiting for another event to occur, that is called waiting state. Ready to run state, if it is waiting in a queue for CPU time. Okay, okay, it is waiting in a queue for a CPU time, that is called ready to run. Okay, and task stack, every task will have stack. Already you know what is meant by stack. Okay, stack is a part of memory. Okay, and it always works on the principle of last in first out. Okay, and for suppose the task is running, if the system gets one very high priority interrupt, then what it has to do, Okay, according to the concept of ISR, interrupt service routine, if the highest priority interrupt uh, occurred, then what it has to do, what are the functions performed by that CPU is saved into a piece of memory called stack. Okay, and the CPU, okay, accepts that high priority interrupt and execute that high priority interrupt some process and return the results, and again it is loaded with whatever the task it is unaccomplished, okay, is again loaded and continue that task, okay, and because of that purpose we use a task stack. Okay, the task stack function is always same. Okay, stack always works on the principle of last in first out. Okay, in that piece of memory we store the data of the currently executing program. Okay, and again it is loaded with interrupt function. Once that interrupt function is completed, okay, the results are returned. Again, it is loaded with whatever the currently running program earlier. Okay, for that purpose, a task stack is required. Okay, that is the task stack. And next one is the context switching and scheduling algorithms. Context switching and scheduling algorithms. See here, what is meant by context switching? Context switching. Okay, already I told you the example as a one, for suppose it executes one program. While executing this program, another one high priority interrupt is there occurred. Okay, when high priority interrupts occurred, what about that current executing program? Okay, what are the results obtained, or what are the data of that currently executing program, and at what state that current executing program is there? All that information is stored into stack, and it is loaded with that interrupt program and execute that program and return the results again loaded with the previous program. Okay, and where the program is halted. Okay, and here that program switches over. Okay, that program is the currently executing program. Okay, and it is goes to subroutine program and complete that program and return the results, again goes to the main program and continue that program. Okay, okay, that is called context switching. That is called context switching. See here, the context switching. The state of the CPU registers where the task has to be preempted is called the context. Saving the contents of CPU registers and loading the new task parameter is called a context switching. That is the concept. Okay, this is the symbolic diagram. Understand? That is called context switching. Okay, the title is okay, quite interesting as a context switching, but the concept is very simple. Scheduling algorithms. What are the different scheduling algorithms? There already you know. Okay, depending upon the requirement of embedded system, the scheduling algorithms need to be chosen as a first in first out, and what are the first tasks occur that has to be finished first. That is the first in first out, and round robin algorithm. Okay, and do all the tasks incompletely. Okay, okay, and first task 20%, second task 20, third task 20, fourth task 20. Okay, again first task 20. Okay, in that's the round robin algorithm. Round robin with priority is also there, and which task having highest priority is executed first. That is called round robin. Okay, shortest job first, and which program having very low execution time. Okay, okay, which task having very highest priority and importance, and based on that Based on that, okay, that is the shortest job first. Only which one is having very lowest execution time? That is called shortest job first. Okay, again, non-preemptive multitasking and preemptive multitasking. This is also very important. I will clearly explain in diagrams. Then it is very easy to understand. Okay, scheduling algorithms. Okay, here we explain in detail as a first in first out. In earlier we okay, uh, okay, we discussed about the scheduling algorithms, but they are very only clock driven. Okay, weighted round robin, and third one according to priority. Okay, and earliest deadline first, and slack time. Okay, of course, all those are covered here also. See here, first in first out, the tasks which are ready to run are kept in a queue, and the CPU serves the task on first come first serve basis. That is the first. That is called first in first out. This is a good algorithm for embedded system. Has to perform well small tasks. Okay, small tasks with a small execution times, and round robin algorithm. Okay, if the kernel allocates a certain amount of time for each task, okay, that is waiting in a queue. Okay, the time slice allocated for each task is called a quantum. That is the smallest piece. Okay, the kernel gives a control to the next task if the current task has completed its work within the time slice. And second one, the current task has no work to do. The current task has completed its allocated time slice. Okay, and based on that, that kernel gives that control. Okay. And next point is the digital multimeters and microwave events use this algorithm in general. Okay. Round robin algorithm also, or weighted round robin algorithm. Okay, round robin algorithm or weighted round robin algorithm or round robin algorithm with priority. Okay, all are same. The round robin algorithm can be slightly modified by the assigning priority levels to some or all the tasks. Okay, example, barcode scanner. Okay, and soft real-time systems can use this algorithm. Okay, why? Because they are not time bounded. Okay, and next one is shortest job first. Shortest job first. Okay, what is meant by shortest job? Kernel always assigns how much the execution time requires. Okay, some key execution time for each task. And based on that execution time, this is executed. The shortest job first task scheduling algorithm, the task that will have minimum time to execute, will given the priority. Okay, this approach satisfies the maximum number of tasks, but some tasks may have to wait forever. Why? Because for suppose in the task scheduling for one task, it takes 2 minutes time, and the remaining 1,000 tasks have less than 2 minutes of execution time. Okay, and according to the shortest job first algorithm, uh, which task is executed by that CPU? Okay, the task which is having a less execution time as less than 2 seconds or less than 2 milliseconds. Okay, whatever that is executed, but that the task which is having 2 milliseconds execution time is waited forever until completion of that 1999 tasks. Okay, that is the problem here. This approach satisfies the maximum number of tasks, but some tasks may have a wait forever. That is the point here. Scheduling algorithms. Scheduling algorithms. Okay. The kernel used in embedded systems can implement a priority-based multitasking scheduling algorithm. Multitasking. Okay. These algorithms are as a two types, as a non-preemptive and preemptive. Okay, already I told you, no. Okay. Here, non-preemptive multitasking and preemptive multitasking. Okay, this is very important, and I won't continue that class, okay, because I have another class. That's why I stopped this topic here. Okay. In the tomorrow's class, I will clearly explain why, because this is very important in exam point of view also. Okay, that's why I will continue this topic preemptive scheduling and non-preemptive, of course, preemptive and non-preemptive multitasking. Okay, in the next class. Okay, thank you, everybody.